So here's our first warm-up. Try that, it'll take about 10 minutes. Pause the video right now. Okay, here's the solution. Did you guys eventually secant cubed anti-driven? Here we go. So I would strongly suggest on trig sub, U sub, you guys are really good at changing limits. Generally trig sub, so I would, anytime you get a trig sub, especially you know one that's going to be hard to integrate, I would go off to the side and, oops. Actually, the minute I actually lied right here. Yeah, this, I just wrote terrible calculus right here. Are those x values or theta values? Yeah, those, actually, I just blew it already. This should be a total indefinite integral. No definite integral. Okay. And so now you should be trying to find the antiderivative, and then once you go off to the side, it's usually good to go off to a different space or draw lines to say, hey, here's a break. After you find the antiderivative, and it's going to be a while, eventually you'll bring it back, and actually that's nowhere close to space. This will be actually way over here. Once you find the antiderivative, then you can say, all right, the antiderivative is over here. All right, that's the idea on a complicated antiderivative. See how you can do it with the secant cube. Be careful with the 1/2. So at that stage, I don't know, should I give you a minute? The overall idea of secant cubed is integration by parts, use an identity to get secant cubed back, and then move the secant cubes together. Now, I have a little bit of a problem with the 1/2 now, which we'll talk about. Ready? Caught up or not yet? Give you another minute. Not yet. Know if you have a question about one of those steps. Actually, I feel like I'm getting robbed of steps here, so. Alright, now we good? Okay, so am I ready to bring that back over and call it my antiderivative from 0 to 4? Or is there a problem? What's the problem? Yeah, we were shooting for the anti-differentiating 1/2 secant cubed, yeah? Okay, so there's two problems with this. First of all, I didn't integrate, I haven't identified this is the answer to 1/2 secant cubed. I have the answer to 1 secant cubed. If I want 1/2 secant cubed, then it must be 1/4 of secant theta tangent theta plus 1/4 of log secant theta plus tangent theta. You down? Okay, what else is the problem before I bring it back and from 0 to 4? It needs to be an x term. So, if 2x equals tangent theta, then a triangle is opposite 2x, adjacent 1, hypotenuse 4x squared plus 1. So my antiderivative is 1/4 of, what's secant? Root 4x squared plus 1. And what's tangent? 2x plus 1/4 log of root 4x squared plus 1 plus 2x. That is our antiderivative. You with me? Now I'm ready to come back and say, therefore, that integral of the arc length of a basic parabola is 1/4 root 4x squared plus 1 times 2x plus 1/4 log of absolute value of root 4x squared plus 1 plus 2x from 0 to 4, yay? Yeah. Cool, here we go, put in 4. I have a 4th root what? 65 times 8 plus a 4th of log of 65 plus 8 minus hope this zeroes out. 1/4 of root the root wouldn't matter because 2x will zero out, yeah? Plus 1/4 of log of 1 plus 0. And log of 1 zeroes out, yeah? Cool. So our answer is 4, nope, 2 root 65. It would be a real shame to screw up based on that. 2 root 65 plus 1/4 log of root 65 plus 8. Now the question is, how do we do? Get out your calculator, check it, let's see if it's right.
Oh, wow.
If it's not right, don't tell me, I don't want to know. I have faith in our calculator. Are we victorious or do we lose? No? We win. We are victorious. Triumph. That's like saying, oh, I could also take a helicopter and drop it down there and see what's the difference. That's all. That's all. Did anybody do that? No, they would probably die. You get the idea. All right. That is rough. That was rough. Okay. Questions on 113? So many questions in the last class. 18. Nine. Did you say 4? No, oh, the answer. I got you. 4. All right. Wow, you guys have a lot less questions. All right, here we go. 18 is okie dokie. Okie dokie. So, let's think visually first. I need to get my act together here. So it looks like this normally, with absolute value, it would look like this, the negative x side being like the positive side. So I'm imagining a sharp turn at 0, and therefore a straight up arc length calculation. First of all, the derivative doesn't have the same rule on either side. Second, the derivative doesn't exist at 0. So I just see problems all over the place with this, yeah? So let's go at this in a piecewise way and strategize. If, trying to think of, do I really need both sides of this? Could I avoid doing the left altogether by just thinking our way through it? How could I? 2 times 0 to 2, and then just a normal 2 to 4. Yeah, I think that would bypass the whole negative side issue. You follow? So now the derivative of the right side is not any different than normal 4 to the x, because positive x's and absolute value of x is the same. So now the question is, do you remember the derivative of 4 to the x? 4 to the x times log of 2 or divided by? It is times. When do you divide? When you integrate, yeah. That's when you integrate. So the derivative is 4 to the x log of 2. And then, sorry, I don't know. 2 has nothing to do with it. Sorry, 4, yes. 2 to 4, 1 plus 4 to the x log of 4. Okay, that should do it. All right, 15. Okay, so 15, a lot of issues here. The number one biggest issue in the last class was people were using their calculator in radian mode to make calculations on this problem, which is in degrees. So that's the first thing we have to deal with. Do you want to convert these to radians or open up a document and put it in degrees, or what do you want to do? Convert them to radians? Okay. How do you convert anything into radians? What's the unit multiplier? Pi to 180. This is actually something you need to do quite a bit in second semester. Now 150, you probably knew that already. That's a reference angle, 5 pi over 6. But the other one, not so much. What is negative 200 in radians? All we're playing with, I guess we could also make it positive if you want. I don't care. Negative 200 pi over 180 is negative 100 pi over, this is why am I making this so difficult, 10 pi over 9, okay? Are you following? Okay, cool. Now, in terms of calculating this, can I just add the magnitudes and add the angles? Can I do that in polar? No, I must add the components. So the horizontal component, how do I find it? No, not Pythagorean theorem, by trig. Negative 4 cosine 5 pi over 6, and add 6 cosine negative pi over 10 pi over 9. For the horizontal component to each vector. Then the vertical is the same, negative 4 cosine of 5 pi over 6 plus 6 sine, cosine sine negative pi 10 pi over 9. Give me a second to put that in. I'll put it in. There's my calculator. Oh, what the heck? There it is. Okay. Negative 4 cosine 5 pi over 6. Geez Louise, pi divided by 6. What the heck? Where's my negative 4? Plus 6 cosine of negative 10 pi over 9. Pi divided by 9. Okay, I got negative 2.174 for the x. Now, I will record that, and I'll probably store it, but I definitely do not want the negative. It confuses the angle. So I'm going to first, I think I'm going to take the opposite of that and store that to I. Oops. Yeah. Okay. Store that to I hat for, all right. I don't like that to be negative because it screws up the inverse tangent calculation. All right, going back up to that there and replacing cosine with sine. Oh, shucks. Okay. And sine. I got, oops, that's not what I expected. Nope. Okay, I get 0.0521. How about you?
Yeah, I got that too.
Okay, store that to J. All right, so here we go. 0.052. All right, now if it said just call it good and rectangular, I would call it good, but it says polar, so I need to do more. It's saying the combination vector is left 2 and up just a wee smidge, 500ths. And I need to find r and theta now. R is Pythagorean theorem with your I squared and J squared. And theta is something like, we're in radians, yeah? So pi minus inverse tangent of J over I. Once I get those done, I will be done. So, shoot. I squared plus J squared. What the heck? What did I do wrong? Did I not store J? Oh man, I don't think I ever stored J. Or I. Do. Okay. Did you get 2.174? I assume. 2.1746. And the angle, I don't know about the back of the book. The back of the book probably has it in degrees. Our radian answer will be something like I minus inverse tangent of J divided by I. 3.117 radians. That sounds pretty good because it's just less than pi, which is where we're on the graph. So that's interesting. All right, answer to 9. Oops. Answer to 9. Let me give me a minute, and I will give you my answer, and then maybe we can talk about choosing a multiple choice. I haven't put that in a lesson yet. I just wanted to focus on doing trig sums. So let me do this real quick, and I'll come back to you. X is sine. So this becomes sine cubed cosine theta d theta over sine squared sine cubed, which is sine squared minus cosine squared. So, negative cosine theta minus plus 1/3 cosine cubed of theta okay. Opposite hypotenuse. So my answer would look something like this. And they made a factor right there, compact. Okay. Alrighty. 4. Is 4 still a question? Somebody need 4? No? Okay. Alright, I definitely don't need definition of derivative properties.
Number 12.
12, yeah, now the answer in the back of the book would be different because they asked for general and I asked for particular. So let's check that we did the particular part right. Oh my, this is so much. Goodness, what a mess. Where did I go? Oh, space. Where did I go? Where is that? Oh, there it is. X, Y squared. Okay, separating variables is no picnic here, so y and y squared on this side, and x squared plus 1 and dx on that side. So this side, when I integrate it, it's natural log of the absolute value of y. And this looks like u sub to me, not trig sub, not arctangent, this u sub. So if I think of 1/2 of 1 over u, I think that's right. And 1/2 log of u, and x squared plus 1, the absolute value is probably not necessary because it's positive. Okay, so that's a start. Now let's get the point in there. 0, negative 2e. Log of absolute value of negative 2e is 1/2 of log of 0 plus 1 plus c. This is log of 2e. Feels like I can do something with that, yeah?
Not just 2. No, it's not. You just get Frank, you
Could
could say.
I? So that's, yeah, that's C. I just thinking, can I clean that up? I guess I could split it. That's fine. All right. At any rate, that's C. So I'm back to this now. I'm losing my absolute value here. Plus log of 2e. And let's finish strong. Dump the absolute value, or the log e to the, do you mind if I move this up front just to clean it up a little? So I got your e to the log of root x squared plus 1 plus log of 2e. I'm going to dump the absolute value in a second, but let's clean up this side. Log plus a log is a product, yeah? 2e to the root x squared plus 1. And if I do that, combine it into a single, then it's just normal 2e root x squared plus 1. Y is plus or minus 2e root x squared plus 1, but based on the initial condition, I don't even remember the initial condition anymore. What was 0, negative 2e? Okay. It must choose y negative. So y is the opposite of 2e x squared plus 1 square root. That wasn't as easy as I thought it would be. Phew, that was nice. Glad you asked. Okay, are we good? 20? Sure. 20, yeah, so I don't know if you guys are just better than I am, but it's possible. I had a freaking hard time learning these when I was your age. I had to suffer through a lot of errors before it started to click. E to the x. Okay, so form-wise, this is e to the 0, so it's 0 to the 0. That is an indeterminate form, so I'm going to proceed with the exponential method, which is e in log. mathematically balanced. Second step, I typically pull the e out front and just focus on what does the exponent do and e it later, and the exponent can come down. Very cool so far. Then, making it, just so we're clear, this is indeterminate. This is 0 times negative infinity, so that's an indeterminate form. I need to make it a quotient. I don't want to make it a quotient because that means now I need x to the negative first in the denominator, but it is what it is. Limit as x goes to infinity of log of e to the x minus 1 is 0. Why did all of a sudden I transitioned into infinity? Sorry about that. Okay, that's log of, so e to the 0 is 1, log of 0 approaches negative infinity, okay? X going to 0 from the positive side, 1 over x goes to, 1 over 0 goes to infinity, so it is. Lo que call problem. I have e to the limit as x goes to 0 e to the x minus 1 for the derivative on the log, e to the x for the derivative on the e to the x minus 1 over negative 1 over x squared. I'm going to clean this up and take a gander here. E to the x over e to the x minus 1. Negative x squared. So let's think about this. This goes to, what does that go to? I was thinking M behavior, but it's not an infinite limit, so it's 0. So this goes to 1 over 0. This is approaching infinity times approaching 0. That's still in a determinate form. That really sucks. Okay, so it is what it is. Here we go again. The limit as x goes to 0 of e to the negative e to the xx squared is, geez, the freaking wings, 0. Limit as x goes to 0 of e to the x minus 1 is 0. So by L'Hopital again. Jeez, what a mess. It's okay. As long as it gets tough, get going, right? So here we go. X goes to 0. Numerator derivative. First stays the same. Derivative of the second. The second stays the same. Derivative of the first. Derivative of the second is e to the x. Now I have an e to the x drop out, I hope, please. E to the x goes to 0. I get negative 2x. Actually,
I'll just go to 0, then 0.
because x is, these are both, you're right, good call. I don't need to take out a common factor. So it's 0 over 1. So all that for 1. Okay, that was a good question. That was from Dinger. But, other question. Alrighty. That was, just another roast on my time for it. Alrighty then. That one is a test of your mettle. Okay. What was that one? I should start that. Oh, man. Let me see if my copy's a little cleaner. Sorry, dark. It is 2. Yeah, the height of that trough is 2 on the homework.
And then the other one's 4.
Yes.